This review video is going to be a very quick one about Bohr models. So, quick review on our periodic table. When you're doing the Bohr models, you're going to have to read group and period information in a specific way. The periods, numbered 1 through 7, remember 6 and 7 repeat down here, provide the energy levels, or the circles, the rings around the nucleus. So the lower down you get, the more rings you have to add on to your model. And whatever their last level is where their valence electrons go. The number of electrons that go into the Bohr model are determined by the number of protons in the atom. That way the atom has no charge. So if it has 11 protons, sodium, then neutral atoms of sodium must also have 11 electrons. This means that you'll have to distribute those 11 electrons on 3 rings, or 3 levels of the Bohr model. Now, the formal rule for determining how many electrons can fit into any given level is 2 times n squared, where n is the period. So the first period can hold 2 times 1 squared electrons, or just 2. If you look at the periodic table, hydrogen and helium are the only 2 elements up there, because that's a very tiny energy level, only holds 2 electrons, so it fills after helium. And that's why helium is a noble gas with just 2 electrons. It can't hold anymore, so it doesn't want to react. It's stable. Second energy level, the second period, can hold 2 times 2 squared, so 2 times 4, or 8 electrons. Again, looking at the periodic table, there's 8 elements going from lithium to neon, with the 8th element being the noble gas, which is stable. Now, the third period is where things start to get a little hinky, which is why in physical science we stop at the end of the third period, because it requires a little bit of hand waving. The third period can hold 2 times 3 squared, I was writing that backwards, 2 times 3 squared electrons, or 18. And now this is why I said things get a little bit hinky. Look at the third period. It fills, or appears to fill, with 8 electrons. And in fact, it does. After those 8 electrons, it moves on to the fourth period, and the fourth energy level. But then it does weird things, and then these 10 electrons fall back down, and crazy stuff happens, and if you want to learn that, take chemistry. So while this can hold 18 electrons, when you're talking about smaller elements, it will in practice fill with just 8 electrons. For example, if I'm looking at the element calcium, well, calcium is in period 4. So I know calcium would have 4 rings in its Bohr model. 1, 2, 3, and 4. Now, before I draw the dots on here, we can figure out how they're arranged. The first level, and before that, let's write down our 20 electron total that we get from our atomic number. That way you can keep track. The first level can hold just 2 electrons, which leaves us with 18 electrons going into the second level. Second level can take 8 of those 18, leaving us with 10 electrons. Now, the third level could potentially take all 10, or all 8 remaining here. But what it actually does is fill with 8, and the last 2 electrons get dropped into the fourth energy level. There's complicated reasons for this, but you can think about it in terms of the groups being similar to each other in valence. So group 1 is a +1. And we'll come back to this Bohr model. Group 2 is a +2. Group 13 is a +3. Notice we're skipping over 10 groups here. Again, 10 just seems to disappear from the periodic table for some reason. And then we have that ±4, which marks the middle, or the half point, of a full energy level. And then we go -3, because you have 5 valence electrons now. And it's easier to get to a noble gas by adding, to -2, 6 valence electrons, -1, 7 valence electrons, and of course the noble gases 0 because they have a complete octet of 8 electrons, 8 valence electrons. And again over here, 4, 3, 2, and 1 valence electrons. Now calcium is in the same family as beryllium, magnesium, strontium, barium, and radium. Group 2, the alkali metals, which means they all need to have a +2 oxidation state, and they all need to do this by losing 2 valence electrons. Well, if I put those 10 electrons all into the third energy level, then I wouldn't have 2 valence electrons, I would have 10 valence electrons in the third level. And so to avoid this, those last 2 electrons as the valence, I drop them into the fourth shell. The easy way to figure this out is to go 2, 8, third period, has to end in 2. How many electrons are left? 8. That's actually a pattern that repeats pretty commonly on the periodic table. This is the electron configuration for calcium. So if I went back and put those as dots into my Bohr model, watch how we fill these 20 electrons. The first level, and I haven't drawn a nucleus in here, so that's my first small circle, holds 2 electrons. I'll put them next to each other. The second level can hold 8. 1, 2, 3, 4. Notice I'm not pairing them yet. Now I'm going to start. 5, 6, 7, 8. So we have 2 here, 8 here. Then I'm going to put another octet worth of electrons into the third. 1, 2, 3, 4, 5, 6, 7, 8. Notice everybody has got a partner. That level is stable, which is why it can move on to the fourth level, or at least a very simple reason for why it can move on to the fourth level. And it has those 2 valence electrons that we know it has because it's in group 2. And we position those on the outside ring, not partnered up, showing that they can both participate in a chemical bond. So magnesium can make a +2 ion. And that leaves us with 2 on the outside ring of the Bohr model. Simpler Bohr models in the first 3 periods, for example, carbon has 2 rings or 2 levels of electrons. It fills in the first one here, the second one here, and then it will go 3, 4, 5, 6. I have 6 total electrons. 1, 2, 3, 4, 5, 6. And I have 4 valence electrons. 1, 2, 3, 4. This matches up with the fact that carbon is in group 14, or 4A, and must have 4 electrons on the outside. And that's going to hold true for everything. On the outside of group 1, 1 electron. Group 2, 2 electrons. Skip that chunk of 10, the transition metals. The outside of boron's family, 3, then 4, then 5, 6, 7, and 8. Transition metals are squirrely about their electrons. They don't keep putting them on the outside, they start burying them beneath. And that's why it gets all confused, and that's why we save that part for chemistry. And the inner transition metals, they're even worse. Okay? That's why they're called the rare earth metals. They're almost impossible to separate. Okay? Tune in for the next video, and we will go over some simple balancing of chemical equations.